To fit the profilometer, start by removing the standard specimen bath and replace it with the open-ended bath, with the open end facing the force transducer block. Thread the adapter cable through the hole in the guard. Clamp the adapter on the side of the transducer block, flush to the tricycle block and as far back as possible on the slotted hole. Fit the guard on top of the adapter. Connect the cable to the high-speed data acquisition interface box. Fit a specimen plate, fit the moving specimen, and now we can see how the device works. The device uses in situ tactile profilometry for periodic measurement of the developing wear scar. The probe is indexed along the wear scar, then onto the unworn part of the specimen from just past the mid-stroke position, so that just over half the wear scar is sampled. Every time a measurement is programmed, the reciprocating specimen head is automatically withdrawn to the stroke end furthest from the profilometer. Every test starts with the measurement of an unworn surface, which is used as the reference surface for subsequent measurements. Raw traces are processed by subtracting the reference surface profile from each subsequent profile. An average is calculated for each processed trace. This gives an unscaled measurement of the trace area proportional to the wear volume. As the profilometer is not mounted directly on the specimen's surface, measurements can be affected by deflection of the machine and test assembly. These can be corrected by referring all measurements to the unworn part of the specimen's surface, but a simpler solution is to make sure that the load applied to the specimen assembly during a profile measurement cycle is always the same. As the reciprocating head has to be withdrawn to the opposite end of the specimen to the profilometer, the recommended procedure is to reduce the test load to a low value, say 50 newtons, before withdrawing and parking the reciprocating head, leaving that load applied during the subsequent profile measurement. Having seen how it works, let's now see how we control it. Select File on the toolbar and Load Setup from the drop-down menu. Select the Profilometer configuration file and click on Open. A Profilometer box will appear on the Compen status bar with a white background. Press the blue reset switch on the machine, which resets the emergency stop and activates the load actuator. The profilometer box will turn green, indicating that communications have been established. On the standard page 2 screen, the high-speed data acquisition controls are modified from the standard machine configuration with the addition of boxes for the profilometer. The two systems, high-speed data acquisition and profilometer, are connected in parallel but used in series. High-speed data acquisition of friction, stroke and contact resistance and profilometer measurements are never used simultaneously. The HSD mode box, which is not required or shown in the standard machine configuration, is now displayed. For high-speed data acquisition, The mode is internally paced. For surface measurement, the box is set to Profilometer. Setting the trigger Profilometer box to measure will trigger the surface measurement routine under manual control, as long as the reciprocating head is fully retracted. Manual triggering is only ever used during setup and calibration. Triggering within a test sequence automatically retracts the moving specimen carrier to the end of the stroke before executing a surface measurement cycle. It makes sense to use a test sequence, as multiple measurements taken over a long period of time will provide the most useful information. While a measurement is taking place, the HSD box in the status window changes to cyan, returning to green once the profile is measured. The Profilometer status box will display measuring and will return to ready once the measurement is done. Setting Profilometer reference to on indicates to the software that the measurement taken is the reference measurement. All subsequent measurements will then be taken with the Profilometer reference set to off. The graph menu now lists a new entry. Selecting Profilometer graph will display a graph on the screen showing the surface measurements. This graph is similar to the standard high-speed data acquisition graph. Once a measurement has been taken, the graph is automatically updated. As with the standard high-speed graph, the y-axis of the profile trace can be rescaled via the Setup menu and selection of a minimum and a maximum value. An example test sequence file is installed. This can be modified to suit specific requirements. Select Test Sequence and select the Profilometer Test Sequence file. Two new columns are added to the standard test sequence file. The Trigger Profilometer column is set to measure every time a measurement is required. The step time is set to a nominal 2 seconds. This is to ensure that sufficient fixed time is available to trigger relays controlling the measurement. The actual step time will be the time taken to execute the measurement. The test will automatically pause, the reciprocating head retract, and the measurement be performed, after which the test will automatically resume. Under no circumstances, press the Next Step button on the control panel to override the test sequence while a profile measurement is underway. Depending on the action programmed in the next step, this action could potentially cause the moving specimen carrier to crash into the profilometer stylus. The profilometer reference column is set to on for the first measurement and then set to off for subsequent measurements. Note that the HSD mode column is set to profilometer before steps where the profilometer is to be triggered, and to internally paste for steps where high-speed data is to be triggered. This example test first heats the specimen to 100 centigrade and takes a reference measurement on the unworn specimen surface. After a running in step of 1800 seconds at 10 Hz with 50 newtons load, the first profile measurement is taken. The test load is then ramped to 500 newtons and measurements taken at progressively increasing increments of 300, 600, 1200, 2400, 4800 and 9600 seconds. Hence, measurements at 3000, 9000, 21,000, 45,000, 93,000 and 189,000 cycles. Note that although the test load is 500 newtons, profile measurements are performed at an applied load of 50 newtons and the test is run at constant temperature to avoid any offset due to thermal expansion. Open a data file before running a test. A profilometer data file containing all the measurements taken during the test will automatically be created. The file will have the same name as the low-speed data file, followed by the suffix P. A hyperlink will be created in the data file each time a profile is measured. The three available on-screen graphs, low speed, high speed and profile, can be opened at the same time. Press Start to run the test. The test preheats the specimen to 100 centigrade. A preload of 50 newtons is applied. Then a reference profile measurement is taken on the unworn plate and the profile graph is updated with this reference measurement. The sequence continues with the running in phase, at the end of which high-speed data is taken and the high-speed graph updated. Then the first profile measurement is taken, adding a second trace to the profile graph. The test load is ramped to 500 newtons, and at the end of the next running phase, high-speed data is triggered and the graph is updated. The load is reduced to 50 newtons and a new profile measurement triggered, with the trace added to the profile graph. At the end of the test, open the data files. A macro is provided to process the profilometer data. Select Phoenix Tribology from the toolbar and click on Profile to run the macro. Raw traces are processed by subtracting the reference profile from each subsequent profile. The macro will plot all the traces on a graph and reference each trace to the relevant number of machine cycles. A second graph will be created showing the evolution of the unscaled wear volume during the test. Finally, graphs of the intermediate measurements are generated showing pairs of traces in sequence. The profile files can be opened via the hyperlinks in the low-speed data file or processed manually if required. Now let's look at the data and see what we can learn from what we've recorded. Note that the wear sensed may be negative, indicating adhesive material transfer from the moving specimen to the fixed specimen plate. Adhesive transfer will frequently be accompanied by higher levels of friction compared with mild abrasive wear. In this example, the fully formulated lubricant prevents adhesive wear. An average is calculated for each zero reference trace. This gives an unscaled measurement of the trace area, which is proportional to the wear volume. Sequential traces and corresponding high-speed friction traces follow. In this example, Mobile 1 produces mild abrasive wear during running in, with material efficiently removed, resulting in lower friction. With PaO4, much more severe adhesive wear is evident, with material transfer from the moving specimen to the fixed plate, the generation of a large wear scar on the moving specimen, and apparent negative wear on the plate. The friction is much higher, suggesting like material running on like material. This concludes this presentation on the T77 in situ profilometer. For more information, please refer to the manual, and for further guidance and advice, contact Phoenix Tribology.